Hello everyone and welcome to the TLE Eliminators PCD for CodeChef Starters 207. Today we'll be discussing the problems A, B, C and F in Div 2, which I believe were the easiest problems in this set, easiest four problems in the set. Okay, so let's get started. Before we get started, as usual, I'd like to tell you about the TLE Eliminator self-paced courses which are live right now. Um, these courses teach you competitive programming all the way from the basics up to the expert level where you can solve questions in like from the very beginning, teaching you the basics of C++, time complexity, sorting, all the way to dynamic programming, trees, graphs, etc. So based on what your current level is, you can decide, right? You can also see Priyansh's video to decide what level is right for you, and you can go for it. Each course contains more than 40 hours of recorded lectures, more than 100 plus curated practice problems, hints and video solutions for all the problems, as well as doubt support by high-rated coders. So yeah, do check them out. All right. So now let's get started with the video. We'll be discussing the first three and the last problem, which I feel were the easiest. I feel these two were relatively harder, and the solve count is a bit odd, but okay. Okay. So the first question is make subarray, and the question goes, there is a canvas with n total cells. Each cell can be white or black. 1 means it's black, 0 means it's white. We want the black cells to form a continuous subarray. Um, we can only change the color from white to black, but not the other way around. Find the minimum number of changes needed, right? Find the minimum number of changes needed, and n goes up to 100. So even a brute force solution will work here. N cube up to n cube solutions will work. But yeah, so let's take an example. Um, okay, so problem A. Basically, we are given some cells, right? Some cells such that some of these cells are black and other cells are white. So I'll fill in the cells which are black. Okay, so these ones are the black cells, the ones which are filled in, fine. The ones which are whited out, basically these are the black cells, let's say. And we want them to form a contiguous subarray, right? And we can only convert these empty cells into filled cells. That's what we can do, right? So we can only convert zeros to ones. That's basically what we can do. So obviously, the only thing we can do to make a subarray, contiguous subarray, is that we should find this first one, we should find this last one, and everything in between we should fill up, right? Everything in between. So we should fill up here, 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 and here. That's why the answer for this case will be 4, correct? And we just need to output how many we need to fill up basically. Okay, so how do we approach this? Well, well, it's obvious that only the first and last matter, as well as the count of how many are already filled, right? So let's say this is the last occurrence, and this is the first occurrence, right? And this is the first occurrence of a filled cell. Now, obviously, the subarray size between these two has to be filled, which is equal to last minus first plus 1, right? So this much distance which is there, last minus first plus 1, this distance, these many cells need to be filled, correct? But already, as you can see, 1, 2, 3, 1, 2, 3 cells are already filled, right? So in this case, last minus first plus 1 is equal to 7, correct? Minus 3, which are already filled, right? Which is equal to 4, right? So that's all for this question. We need to find last occurrence of 1 minus first occurrence of 1 plus 1, subtract by total occurrences of 1. So count of 1. Okay, so this is our answer. Time complexity, we only need to go through the array once. So time complexity will be big O of n. Okay, memory complexity will also be big O of n. Fine. Let's have a look at code. Look at the code for this. So as you can see, we take in n and the string. We have first, last, as well as black count. Correct. So each si which is equal to 1, which means it's black. Uh, if this is the first one, we set it to I. The last one also we can keep updating to the current position I, and we increase the black count. If the black count is 0, our answer is obviously 0 itself. Otherwise, our answer is this last plus first plus 1 minus already black, right? So minus black count. Okay. So that's about it for problem A. Pretty simple problem. So let's move on to problem B now. Okay, so problem B, um, you're given an array A of size n. The score of a permutation of integers is defined as the following. So if P of I is equal to I for at least one I, the score is -1. Otherwise, the score is the number of indices such that A of P of I is less than or equal to A of I. Okay, so the score is equal to number of indices such that A of P of I is less than or equal to A of I. Find the maximum possible score, and some examples are here. Okay, so first we'll try to understand what does it mean for A of P of I to be less than or equal to A of I. Okay, so also n goes up to 10 power 5, so big O of n constraints, right? Okay, so let me just make a given array. Like, for example, I have an array which looks like this. Okay, so let's just deal with sorted arrays for now. So it's simple. The total number of elements here, as you can see, is 8. So we need a permutation consisting of the numbers 1 to 8 as our answer, correct? Now, let's say this was the permutation. Okay, let's say we have the most basic permutation 1, 2, 3, 4, 5, 6, 7, 8. Now, obviously, since the second condition is satisfied, that A of P of I is less than or equal to A of I. Why is that? Because A of P of I is simply 1. A of I is also 1 here, right? And obviously A1 is less than or equal to A1. Similarly, A2 is less than or equal to A2, so on. But the first condition is not satisfied. The first condition says P of I should not be equal to I, basically, right? Otherwise, the score will become -1, and we don't want it to become -1. So the first condition says P of I. Basically, we should avoid making P of I equal to I, because otherwise the score will be -1. Correct? So P of I should not be equal to I. Obviously, there will be permutations with P of I is not equal to I. So the score will always be greater than -1 for them. Correct? So we should avoid this. We should avoid this. Right? So now what do we do? Um, One thing we can do is we want P of I not equal to I. Also, we want A of P of I less than or equal to A of I. Correct? So what we can do is we can always put the value just lesser in our permutation so that A of P of I will be less than or equal to A of I, and we will get our condition. Okay? So what I mean by this is for I equals 2, right? We'll put 1 in the permutation. Okay, we'll put P of I equals 1. For I equals 3, we'll put P of I equals 2, and so on. So basically what we're doing is we're putting the permutation like this. We're putting the permutation like this. Basically, we're going to write the permutation as 1, 2, 3, 4, 5, 6, 7. And obviously 8 is left over, so we put it here. Correct? Now, as you observe, first thing which happens is never is P of I equal to I, right? Because here always P of I is equal to I plus 1, sorry, I minus 1. And here P of I is equal to n, right? So never will this happen, right? So we're safe from that way. Now, second thing, if you observe, since it's always pointing to an element which is lesser than it, right? It's always pointing to an element which is lesser than it. Um, A of P of I is always less than or equal to A of I, right? We're always pointing to an element lesser. So one is pointing to this one is pointing to this one, this 2 is pointing to this one, this 3 is pointing to this 2, so on. That's what's basically happening, right? So since 3 is less than or equal to 2, right? So 3 is equal to A of I, and A of P of I is equal to A of 4, right? This is A of 5. So as it's sorted, A of 4 will be less than or equal to A of 5, right? But this only holds for sorted array. This holds for sorted array. But for unsorted also we can do the same thing. But for unsorted also, same thing we can do basically. All we need to do is for each element, just put the element just before it in sorted order, right? For each element A of I, let A of j be the element just before it in a sorted order, in a sorted order, then put um, P of I equals j, correct? P of I equals j. Then we have the first condition satisfied, P of I is not equal to I. Also then A of P of I is less than equal to A of I, correct? So both the conditions will hold. Obviously, this trick works only for numbers which are not the smallest number, right? Because otherwise there'll be no number before it in sorted order. So we can say that this trick works for all these numbers which are not the smallest number because we can put something smaller than it. So always the answer will be greater than equal to n minus 1. Okay, the answer will always be greater than equal to n minus 1 by this method. Okay, okay. Now the only option now is to make the answer equal to n. Okay, when will the answer be equal to n? And when will the best be n minus 1? So for n minus 1, we already found a way to construct it. We simply put the element before it in sorted order, right? So how do we find answers equal to n? Well, obviously, if you take the example over here of, even if you see the example, if all the elements are equal, if all the elements are equal, then we can just, we get an answer of n because directly what we can do is we can just take this one and put some other one over there, any a of I not equal to I, correct? So we can put something like, for example, we can put, for this example, we can just put like this, right? Just cyclically rotate them or something like that, right? Or we can even put the original way. So we can put it like this, right? As long as it's equal to some other element, all the elements are less than equal to a of j is less than equal to a of I, right? Because all the elements are equal itself. Another example where we can always get the answer n is where, and this is a interesting and important case, is where we have multiple elements like this, right? Here we can always get the answer equal to n. How? Because see the I values over here are 1, 2, 3, 4, 5, 6, 7, 8, 9. So the P of I values which we can choose will be simply, for example, we can choose 4, 1, 2, 3, 7, 5, 6, 9, 8. Why so? Because these ones are equal, right? So by making them point at each other, we're making this one point here, we're making this one point here, this one point here, this one point here. By making them point at each other, what is happening is A of P of I is equal to A of I basically. So it's satisfying the condition of A of P of I less than equal to A of I. It's also satisfying the condition P of I not equal to I. Correct? It's satisfying both the conditions. So if each element has a duplicate, okay, if each element has a duplicate, if each element has a duplicate, then answer is n, at least one duplicate, at least one duplicate, then the answer is n. It can be more than one also. Otherwise, answer is n minus 1. And n minus 1, we can use the above construction. And for n, what we can do is we can just use the cyclic shift on elements which are equal, right? So we just need to find the, for n solution, elements which are equal, we can do a cyclic shift. To do this efficiently, we can simply use a map from each element to a vector of int of their positions. Okay, so map from int to vector of int. So what will be the time complexity of such a solution? Time complexity will be simply big O of n log n, since we're using a map, correct? The memory complexity will be big O of n itself. So for each, for the n minus 1 solution, right? That means that some element does not have a duplicate, then only we do the n minus 1 solution. We just cyclic shift on the whole array. Otherwise, for the big O of, for the solution where the answer is n, that means that each element has a duplicate. For each value, we need to cyclic shift on that value. We can use a map of int and vector int to do that. So let's have a look at code for this. We input the value of n. Also, we input all the vector pairs. Here, the first value of the vector is its value. The second value is its position. Similarly, in the map, for each value, we push back its positions in the map. Now we are checking if there is a element which appears exactly once, right? So element which does not have duplicates, or an element which appears only a single time. So single is false. If the size of the vector of its occurrence is equal to 1, single will become true, right? It's going to be our answer permutation. If it's single, then we can just sort the elements. Each element will be equal to the previous element's position. Okay, so each element in the permutation will the position to the previous one in sorted order position. Because it's zero index, we're doing plus 1 over here, right? So each element a of I has a position a of I dot second. Its value will be equal to the position of the previous element in sorted order plus 1, right? From all the elements from 1 to n minus 1. And the first one will be the remaining value, which is a of n minus 1, right? Position. So this is for the case where there's one value which appears exactly once. For the other case, we have to do cyclic shifts of this vector v. So for each xv, we find the vector v's size. We go through this, and each v of I will be set to position plus 1, where it is equal to the cyclic shift, right? So it's going to equal to I minus 1. And if I is equal to 0, it's going to be size minus 1, right? So we're doing a cyclic shift on it. We're setting the position. Now, if it's single, the answer is n minus 1, otherwise it's n. And we can output this permutation which we constructed, right? So that's about it for the question. Yeah. So let's analyze the type complexity, memory complexity. Type complexity is big O of n log n because we're using a map and we're doing map insertion. And we are using sorting as well. So obviously the type complexity cannot be made better because we need to sort. And the memory complexity of this can be big O of n. Okay. So now let's move on to problem C. Okay, let's move on to problem C. Let's go ahead and read the question. An array A of size n greater than or equal to 2 is called good if the following conditions hold. If basically what's written is if each element is equal to 0 or the sum of its adjacent elements. Okay, so if each element is equal to 0 or it is equal to the sum of its adjacent elements. Uh, so what we need to find is in one operation, if we can add one or subtract one from some element in A, and we have to find the minimum number of operations to make array A good. We can prove that it's always possible, right? N goes up to 10 power 5, so normal constraints. Okay, so let's go analyze this question. First of all, expected type complexity is big O of n or big O of n log n. Okay, because n goes up to 10 power 5. Okay, now the given constraint tells us that basically, let's understand what our final good array looks like. Okay, so good array, each element is either 0 or sum of adjacent elements. It's either 0 or the sum of its adjacent elements. So obviously an answer always exists. So we can show that the answer always exists because obviously we can have an array in which all the values are converted to 0. Right? So we subtracted 1 from all the values and we converted all of them to 0. So obviously the answer always exists. So now what is the given condition? The condition is that for a of I which is not 0, a of I is equal to sum of a of I minus 1 plus a of I plus 1. Right? So it's equal to the sum of adjacent elements. So now how do we satisfy this condition for every element? Right? For every a of I not equal to 0, we have to satisfy this condition. Right? Then only it is good. So assume that, let's say some elements are 0, right? And then the first positive element is x. Okay, the first positive element is x. Now, what can we say about x? So x will be equal to the sum of these two adjacent elements. Correct? X will be equal to the sum of these two adjacent elements, and that means x is equal to 0 plus this next element, whichever is next element, right? So that means that the next element is also equal to x, right? And then, so we have that these two x will appear as like a pair, right? Now, what about this next element, right? Now, this must also be 0, correct? This must also be 0 because this element also has to be equal to the sum of adjacent elements, correct? So that's why we get that our array in the end is going to look something like this, okay? Our array in the end is going to look something like this, where there are some pairs of numbers separated by a bunch of zeros, right? Some pair of numbers separated by a bunch of zeros. So in particular, either the ith position, either the ith position is a zero, or it forms a pair of equal elements. Okay, so that's what happens. So how do we do this? How do we find the minimum cost? So part two of the question is now, how do we find the minimum cost? How do we find the minimum cost to achieve this, right? To achieve this, right? And for this, our intuition is that since we have exactly two choices at each situation, right? Uh, at every position I, at every position I, we have exactly two choices: convert it to 0 or a of I equal to a of I minus 1 and a of I minus 2 is equal to 0, right? So in these two choices, what we can do is, since we have only two choices and we need to take best or minimum cost of both of them, we can use the DP, correct? We can use dynamic programming. Use dynamic programming. Okay. What will be our transition? Our transition will basically be a of I is equal to the cost to convert it to 0, right? Sorry, dp of I is equal to the cost to convert it to 0. So dp of I is equal to min of the two options. One option is we convert it to 0, so that will take a of I because we have to subtract a of I times plus dp of I minus 1, right? So we have converted this to 0. Now we need to find dp of I minus 1. Otherwise, we have made these and the previous element equal, right? We have made this one and the previous element equal, so the cost of that equal plus the cost of converting a of I minus 2 to 0. So that's a of I minus 2 plus dp of I minus 3. Correct? So minimum of these two. What will be the cost? So if we want to make two elements equal, right, like 3 and 5, what we can do is we can make them equal to the midpoint, right, which is equal to basically 4, right? So this will be one from this side, one from this side, right? So basically the equality will be the difference between them. The equality will be the difference between them to make them equal. So we can do is, what we can do is we can write abs of a of I minus a of I minus 1, right? So this is our DP transition. All right. Now what is the base case? So obviously our DP will have a base case. Obviously, the base case is the first element becomes 0, so that will be A of first element becomes 0. Will be dp of 0 equals A of 0. Then we can do this transition, and our answer will be simply the minimum cost for the whole array. So our answer is dp of n minus 1. Alright, so this is the base case dp transition. Simple 1D dp to count how many ways we count the minimum cost to make it equal to good array. Right? So let's have a look at the code for this. Type complexity will be obviously big O of n. Right? Big O of n. We're not doing any log factor also. Just direct dp array. Okay. So first we take in array A. Our base case dp of 0 equals A of 0. Uh, dp of I equals A of I plus dp of I minus 1. Right? So this is the first case where the current element becomes 0 and we take dp of I minus 1. Now if I minus 1 is greater than or equal to 0, we can take the second case. So we take the absolute value difference, right? And if there exists a previous value, that value must become 0. So we do A of I minus 2. If there exists a value before that, then we can add dp of I minus 3, correct? So dp of I will become minimum of dp of I and this value. Finally, this will find us the global minimum at dp n minus 1. So we can print that, right? So pretty straightforward 1D dp question. All right. So now we can move on to problem F. The problem F, which is balanced subarrays, correct? So in div 2, this is problem F. In div 1, this is problem D, right? So we can move on to problem F, which is balanced subarrays. Balanced subarrays. Okay, so let's go ahead and read the problem. An array N, an array A of length 3n is said to be balanced if it contains exactly n occurrences of each of 1, 2, 3. For example, 1, 2, 1, 3, 3, 2, and 3 to 1 are balanced, whereas they've given some examples of unbalanced arrays also. As you can see, one appears twice, 2 appears twice, 3 appears twice, right? So basically 1, 2, and 3 appear equal number of times. Okay. You're given an integer k, which is from 1 to 10 power 7. We have to construct an array A of length at most 10 to the power 4, which has only the integers 1, 2, and 3, such that it contains exactly k subarrays which are balanced. Okay. So exactly k subarrays are there such that they have equal number of 1, 2, and 3. It can be proved a valid array always exists. Note, you don't need to minimize the length of the array. It just needs to be less than or equal to 10 power 4. Okay. If there are multiple possible solutions, any of them will be accepted. Okay. So, um, so there are some examples over here, like for n equals 1. So we need to make an array which has exactly one balanced subarray. So that's obviously 1, 2, 3. And for n equals 2, we need two balanced subarray. So there we have an example of 1, 2, 3. As you can see, another one, 2, 3, 1 is also being formed, right? Okay. So let's go have a look at how to solve this, right? Constraints k less than or equal to 10 power 7. And obviously they said n has to be less than or equal to 10 power 4. Okay. So we can do big O of k, right? If we do exactly big O of k, we can have a solution. First thing we can think of is, since we need balanced subarrays anyways, we can try and make it using the given balanced subarray like 1, 2, 3. It's the most basic balanced subarray, right? And it adds exactly 1 to our answer. What about 1, 2, 3, comma 1, 2, 3, right? This also adds some number of balanced subarray to our answer, like this, 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 right? So all these subarrays are balanced and they get added to our answer, correct? There's also so if you have more 1, 2, 3s, you can form many more over here, right? So here I think 5 are being formed. 1, 2, 3, 4, and the whole array, which is the fifth one. Correct? So 5 are being formed total, which are balanced. So we need to form one with exactly k balanced subarrays. Okay? Exactly k balanced subarrays. So one idea we can have is that um basically what if we use some groups of 1, 2, 3, 1, 2, 3, right? And then we concatenate them, right? We concatenate them so that we get exactly k balanced subarrays, and we can put maybe something in the middle which is unbalanced, right? We can put them something in the middle which is unbalanced so they can be separated, and we can put something unbalanced in the middle. So that is one way we can do it. And so for this we need to figure out, this is just an intuition, right? So for constructive problems you need to try a bunch of cases, you need to try what works, you need to see what works. So this is one idea that you would get maybe. Obviously there are many ways to solve this since it's a constructive question, but yeah, what you can do is you can say that, oh, okay, I'll put like some balanced blocks followed by unbalanced, followed by some balanced block, right? And for an unbalanced block, we can just maybe put one number multiple times, something like this. And so it becomes unbalanced, correct? Okay. So then, if you see only the number 1, 2, 3, then the number of balanced subarray here is 1. If you see 1, 2, 3, 1, 2, 3, the number of balanced subarray here is 5, right? And what about 1, 2, 3, 1, 2, 3, 1, 2, 3, right? So how many will be there? We don't know. So what we can do is we can try and figure it out, right? So from each starting one, right? If we start at a one, then we can end at each possible three basically, right? We can end here, 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 right? And from this one we can end here, here, right? And from this one we can end here. And all of these will be balanced. So for the one, um, so let's say we have repeated 1, 2, 3 n times, or maybe we have repeated it I times. So for I equals 3, the number of balanced subarrays starting at 1 will be I choose 2, sorry, I plus 1 choose 2. Okay, so let's calculate how many ways we can start at a 1 and end at a 3. So from this one, we can do it in one way. From this one, we have two possible 3s, right? And from this one, we have three possible 3s to end at. So basically, we get 1 plus 2 plus so on till I, which is obviously equal to I times I plus 1 by 2, correct? Now, what about the subarrays which start at 2 instead, right? The subarrays which start at 2 instead. So we can have starting at 2, ending at this one, or ending at this one, right? And then starting at this 2 and ending at this one. So we get 1 plus 2 plus so on plus I minus 1, right? So we can write that as 1 plus 2 plus I minus 1, and this is equal to I times I minus 1 by 2, correct? So this is for the subarrays which start at 1. This is for the subarrays which start at 1, end at 3, because these will be balanced. This is for the ones which start at 2 and end at 1, which will also be balanced, right? Because we need an equal number of 1, 2, and 3. Similarly, we'll have start at 3, end at 2, and that also, as you can see, start at 3, end at 2 is the same thing again. So it'll be 1 plus 2 plus I minus 1 again, right? So we'll get 1 plus 2 plus I minus 1, right? So we get this. So what is the sum of these three? That is the total number of balanced subarray of 1, 2, 3, 1, 2, 3 repeating. So for the repeating pattern 1, 2, 3, 1, 2, 3, so on, which repeats I times, which repeats I times the balanced subarrays, the number of balanced subarray is equal to I times I plus 1 by 2 plus I times I minus 1 by 2 plus I times I minus 1 by 2. Right? Here it's minus 1 by 2. Okay. So this is the formula. Now let's simplify it. So we get I by 2 times I plus 1 plus I minus 1 plus I minus 1. This 1 will cancel. So we'll get I times 3I minus 1 divided by 2. Right? So this is formula for the balanced subarrays within this uh, given repeating pattern. Okay. So how do we use this to find our answer? So basically we can come up with this approach, which is basically for a given k, while k is greater than 0, right? While k is greater than 0, what we can do is we can repeat for the maximum, for the max I, such that I times 3i minus 1 by 2 is less than or equal to k. We can repeat 1, 2, 3, 1, 2, 3 that many times and append it to the array, append it to the answer. This is a very constructive problem, so you need to come up with the idea, kind of with a little bit of guesswork, right? So we append this 1, 2, 3, 1, 2, 3 the array, and it gives us feeling like this will give us the maximum bang for our buck, right? This is giving us, like greedily, it's giving us the most amount of values which we can get, and we append it to the answer. And now we can pad it, right? We can put a separator if needed, put a separator so that, let's say if we have 1, 2, 3, 1, 2, 3, and we also have another 1, 2, 3, they should not form balanced subarrays across each other, right? So we need a valid separator. And if you observe, uh, try out some separators, you will see that 2, 2 is a valid separator. Why is 2, 2 a valid separator? Because if we put only 2, for example, if we put only 2, then it can still form a balanced subarray with some numbers. Similarly, if we put only 3 or only 1, right? And if you put 1, 1, what happens is this 1, 2, 3 forms a balanced subarray, so we don't want any extra ones. That's why we're putting 2, 2, since it's the middle value, and we repeat it twice, so it makes sure that it's unbalanced, right? It makes sure that this one is unbalanced. Okay. So basically, while k is greater than 0, find the max size such that I times 3i minus 1 by 2 is less than or equal to k. Append this repeating pattern to the answer and put a separator, right? So, and now what we can do is we can subtract um, this value, subtract I times 3i minus 1 by 2 by from k, because that many new balanced subarrays we have created, right? And we repeat this while k is greater than 0, right? So this is our guess so far, right? Guess so far. Why is it a guess? Because obviously it will give us an answer, but it will give us a valid answer, obviously. But the question is still to prove, still to prove that the total length of the array will remain less than or equal to 10 power 4, right? That question said that the total length of the constructed array should be less than or equal to 10 power 4. So we still need to prove that. Okay. So first, let's just have a look at the code for this. Um, then we'll prove this remaining part. Okay. So let's have a look at the code. We take in k, we create a vector of answers. If the answer is not empty, that means that there's already something there. We need to push a separator. So we push back 2 and 2. Okay. Now we are finding the largest I such that I times 3i minus 1 divided by 2 is less than or equal to k. So I equals 1. While this is less than or equal to, we do I plus plus. And at the end, we do I minus minus because it has just overshot, right? Now we can subtract k with this value, I times I 3i minus 1 by 2. And we can repeat I times and we can push 1, 2, 3 back to the array, right? So 1, 2, 3, 1, 2, 3, we're pushing this pattern. Finally, we can simply print the size of the answer, print the answer and go to the next test case, right? So this is the implementation of our construction, and the time complexity will be obviously big O of k times. So it won't be big O of k; it will be obviously a bit lesser than big O of k, and it will basically be the time taken for roughly the number of elements, right? But we can say that it's bounded by big O of k. The time complexity will be at most big O of k, so we can write that for sure. Probably it will be much lesser than big O of k because we're subtracting from k again and again large numbers. But at most, the time complexity will be big O of k. Okay, so we can write um, less than equal to big O of k, big O of k, or probably lesser, right? Probably lesser because we're repeatedly subtracting. Okay, so now we need to do the remaining part, which is that we need to prove that the total size of the array made here is less than equal to 10 power 4, right? And obviously you can try to do this mathematically, but that takes some time. Or you can just go with the guess and try to do proof by AC, right? Proof by AC just means that you submit and you check if it works or not, right? Or what we can do is we can make a simple DP, just for our reference, not for the code which we're submitting, just to check if this works. So for every k from 1 to 10 power 7, we can have DP of I equals basically the number of elements. So the separator will be 2, I plus 2 for the separator. Sorry, j plus 2 for the separator. J plus 2. J is the number of elements added plus dp of I minus j times 3j minus 1 by 2, right? So we can use this following dp, and max of dp of I will be the longest length array formed, right? So this is a dp to calculate the length of the array formed with our solution, So we are using this dp to calculate what the max would be. So let's have a look at the dp. Um, n max or k max is 10 to the power 7. So we have that here. We make our dp. We want the maximum value within the dp, correct? So that's why we are storing this max file. Then for every I, we are finding whichever j times 3j minus 1 by 2 is less than equal to that I. Once we find that, we do dp of I equals dp of I minus this much plus 3 times j. And if this is not 0, right? So if it is not the starting element itself, then we have to add the separator, which is dp of I plus equal to 2. Now we take max of all of this. If you run this code, so I just ran this code over here on the terminal. As you can see, the maximum length which we got is 8,000, which is conveniently less than 10,000, right? And now you might ask, okay, how did you get so lucky that 8,000 you got, which is less than 10,000? Um, so basically the process was that you first think of the pattern, right? First think of the pattern of filling. And obviously your intuition should tell you that this pattern of filling should be good because it's making a lot of balanced subarrays, right? It's making a lot of balanced subarrays, right? And the code for this implementing this pattern is also pretty simple. Code is simple, right? And then once you have this pattern, you guess this pattern, you can check if it satisfies our condition of less than equal to n or not using dp, right? In this similar way, you could have come up with other patterns. Instead of 1 2 3 1 2 3, you might have come up with some other pattern like 2 1 3 2 1 3, something like that. And then you could have counted in that as well, chosen a separator in that. Or you could have come up with a completely different pattern. Either way, if the pattern is valid, you can use some kind of DP or some kind of mathematical proof to check if it gives you less than equal to the maximum number of elements, which is 10 power 4, right? Um, yeah, 10 power 4 is 10,000, 8,000 is definitely less than 10,000. So we are happy with the solution and we can go ahead and submit it, right? We can go ahead and submit our solution. So here we use an important trick, which is using another code like this DP code to prove that our solution for this code is correct. So now we can go ahead and submit it. And as you can see, this submission passes, right? This submission passes. All right, then that brings us to the end of this session. we discuss problems A, B, C, and F in Div 2, or in Div 1, we discuss the problems which are A, B, C, and D, right? I feel like these were the easiest four problems of the set. That's why we discussed these problems. Thank you for watching. If you didn't get any part, just first rewatch that section. So you can go ahead and read the editorial as well as try to learn from multiple sources. That helps, right? And also definitely upsolve at least one question which you could not solve in the contest, right? Uh, Thank you and see you in the next PCD. Bye bye.